Welcome to lecture 22nd, and we are discussing about efficiency of transformers, and there are efficiency which is called power efficiency. As you know, we at a degree of loading x is I am writing many a times, so that it really you always remember this. So, x s and based on this I can tell so many things, x square P C U full load plus P core. And what I saw with this expression of efficiency is this thing, that you at a particular power factor, if you sketch it, it will be like this, and this is efficiency eta, and this is the load at which maximum efficiency will occur, P core by P C U full load, and this is your x, this is eta max. This was found, and I told you also, this is important to note, that this curve has been obtained at what fixed power factor. So, tag that 0.8 power factor. Now, the question is power factor of the load may also change. Suppose I repeated the same exercise, I want to get the efficiency versus x curve for say 0.6 power factor or unity power factor or 0.2 power factor. How this efficiency versus x curve will change? Will its position will remain same? I am not sure right now, but I am sure about one thing. Whatever be its position, the value of x at which maximum efficiency will occur, it only depends on P core and P copper full load. It will be here only. Now, let us see how to then find out what happens if cos theta also varies. How to find out this? Okay, that is what this problem can be framed at this way. I will frame the problem. This is your efficiency curve. At a given power factor, say cos theta. What I am going to do is now, I will fix the load on the transformer. That is, I will see that kVA, I want to see the effect of variation of power factor angle of the load on efficiency, that I want to do. So, to do that, what I will do, this is my x, no doubt. I will keep this x fixed and vary theta. So, at a given power factor angle, suppose at a given x, this I will now, this vertical line I will keep fixed, line fixed, means what? X into s, this I have fixed. I am not now going to vary x and vary theta in this expression. Got the point? That is what I mean. Efficiency is now x into s cos theta divided by, for a given kVA, x s cos theta plus x square PCU full load plus P core. This is the efficiency expression. What I am telling now, to understand how this curve, how efficiency will vary if you vary theta, what I have done is I will keep this constant. At a given kVA, I want to see, okay, I will vary power factor at this kVA. What is this kVA? A fixed value of x into S. X is fixed now, I will fix x and then vary theta. That is what I will do. Power factor I will vary, and I want to see at a given fixed power factor, at a given kVA, then I will be able to tell at what power factor efficiency will be maximum. Now, this thing, that is what I will do next is this expression I will do d eta by d theta. In this expression, in this modified problem statement, what I am telling, P code is fixed, x square PCU fuel fixed, because I am not going to change x, I will be on this line only, fixed. I am not going to vary x at a given x, excess kVA the transformer is handling, tell me at what power factor efficiency will be maximum. So, to do this, xs I will keep fixed, that is this line, x is fixed, keep x fixed and vary theta. Other things are fixed, x being fixed now. So, it will be not very tough if you set this to 0 and see that, prove that, this is prove, show that, not prove, show that, so that eta will be maximum when cos theta is equal to 1. This is the thing. You go on very, for a given kVA, this is corresponding to say 0.8 power factor. What this expression will tell you, this efficiency will be maximum when cos theta equal to 1. That is, at this point it must be above this curve. Therefore, I can now draw. So, this you please try to prove on your own. You have to simply differentiate it and show that okay, at a given kVA, that is what I am telling, this is the transformer. You always pass a given fixed current by varying the load, but in this case I will vary only cos theta to change the magnitude of the load, and then I am telling if it is the unity power factor, then efficiency at this fixed load as you vary theta power factor, efficiency will be maximum here. In other words, next page I will draw. This is quite interesting to note that now I can complete this efficiency versus x curves by drawing a family of curves. Suppose this is at cos theta is equal to 0.8. What I am telling, the curve will be above it and you draw a vertical line here. This will be corresponding to cos theta is equal to 1. It will be above cos theta equal to 0.8. If cos theta equal to 0.6, it will be this. You can draw a family of curve. Now, showing really that is, I am not now restricting that cos theta is 0.8. Okay. Now, the full picture is clear to me, but nonetheless that is this thing remains this one, P copper full load, and these maximum efficiencies are corresponding to different power factors. Eta max at 0.6, eta max at 0.8 is this much, and this is eta max at 1 unity power factor. So, this axis is eta efficiency. Now, we come to know, oh, the transformer will have maximum efficiency, possible efficiency this much. At 0.8 power factor, okay, if that 0.8 is kept fixed, that will give you some maxima. But you can still operate the transformer at higher efficiency than this, provided your load is unity power factor. Got the point? This is the highest maximum efficiency possible, eta max highest. This is an interesting point to note, that is at unity power factor. But nonetheless, whatever be the power factor, the load at which this maximas will occur, that is fixed. So, this curve, a family of curves, now bring out the total picture of what is going on in a transformer when you are changing load, both power factor and impedance. So, highest possible efficiency is when you say the load on the secondary of the transformer is resistive, unity power factor, then only you will get the highest efficiency. Okay, for a given power factor, if the load power factor is 0.8, it will still give you maximum efficiency here, but that will be lesser than the maximum efficiency, which is still possible if the impedance is purely resistive. That is what I want to tell. But here is a catch. The catch is the load on the secondary of a transformer will be several kinds of motors. In industry, this will supply some motors. Motor means RL. There will be other RL type of load. RL type of load are most common load. That is not in my hand, is not. You must be knowing that the load power factor, people try to maintain it at say 0.8 is a good number. Okay, you connect RL load, this that load, but try to see the power factor is close to unity, but at least 0.8. And if your load power factor is below that, then what supply authority says that you will be penalized, because you will be drawing, you are utilizing lesser power out of the total kVA you are drawing from the lines. Therefore, it is the condition imposed by the supply authority that you are the user of electricity, try to see that load power factor is not below this, maybe 0.8 say. And if you are found to draw power for loads which is below 0.8 say 0.6, you will be charged extra. Okay. These are the things which come into play now. But as I told you, unity power factor is not the usual case. So, that is why even if your load is having low power factor, that is why people connect capacitor at the beginning, capacitor at the beginning of your supply, so that power factor is improved. You know those techniques from your circuit analysis and this that. Therefore, although resistive load will be a desirable load to be connected across the secondary of a transformer to have always the highest efficiency for any kVA, mind you, if you are operating the transformer at this kVA, fixed kVA, then you see efficiency will be maximum among these maximas, among this available efficiency at different power factors, that will be maximum. That is a very good thing. So, it is an important point to be noted. Okay, nothing is better than unity power factor load. At whatever kVA it is discharging, you will always get highest this thing, highest efficiency with unity power factor load, and the highest most efficiency will be when the kVA is this much, at this kVA you are operating, and the unity power factor load it is. You must think about this, you think yourself what I am telling. So, that things will these are quite interesting. I mean, there is some logic in that, nothing out of nothing something is being told to you. So, these curves, then I have drawn a family of curves with different power factors. Then I told you, okay, now I will keep the kVA fixed and would like to see these are the efficiency, which of these will become maximum, and you have been asked to find it out that at cos theta equal to 1, you have to differentiate this expression by noting that now you will not change kVA, only power factor you will change, differentiate it, set it to 0 and come to the conclusion that if cos theta equal to 1, that efficiency will be maximum. It is very interesting to note. So, that is all. Now, we will come to as I told you, if in a transformer, suppose here is a transformer, a distribution transformer say. What is going on in a distribution transformer? Here are loads. How the loads are connected? I am a consumer, I will connect my load. All loads are connected in parallel, you know. Here is another consumer, he will connect load like this. There is another consumer, you connect load like this, dot dot dot, and so many consumers. And perhaps when all the consumers, because my habit of using electricity will not be matching yours. So, I will sometimes switch on my load or not, at any point of time that may change, very complicated situation. So far as the loading pattern on the secondary of the transformer is concerned, we really do not know. But what happens is this, with large number of consumers, it is found that okay, there is a general type of variation of load on the secondary of the transformer. When you close these two consumers, then current supplied is this plus this. So, load increases as consumers are connecting their loads, you understand that. Now, the question is in distribution transformer there will be a variation of load pattern over 24 hours. There will be some evening peak, there is some morning peak, offices are open, electricities are used. In the evening, once again, as I told you, there is a peak load demand, because most of the users will switch on their lights and fans and what not. So, there will be a variation of load, and if there is a variation of load, then certainly I am sure about this point, that no point in asking that for this transformer I will demand power efficiency, maximum power efficiency for this transformer should occur at x equal to 1, because at full load condition this is will be operating at some point of times over certain time period, but certainly not for 24 hours. That must be understood before I calculate. That is why this type of transformer should be judged, their performance should be judged not from the point of view of power efficiency, but from the point of view of what is called energy efficiency. Or called all day efficiency. And as I told you, I wrote last time that eta all day is equal to energy in kilowatt hour. You must be knowing energy is in kilowatt hour supplied to the load over 24 hours. Load in a day, that is over 24 hours. That is why it is called all day efficiency, divided by input energy to the transformer, input energy to transformer, in a day, in the same day, in a day, that is over 24 hours. Very simple calculation, nothing very complicated. Okay. Now, so what it is? What are the informations needed to find out the energy efficiency? So, suppose I say that this is the primary. Mind you, a distribution transformer, this primary is energized for 24 hours, okay? V 1 whatever is the voltage at frequency f. In distribution transformer, primary must be kept energized for 24 hours continuously for 24 hours. It must be, because you do not know when your consumer wants power, that is not known to me. I must be ready at their doorsteps with power available. Whether they will use it or not, that is their botheration, I do not know. Now, suppose I say I have to do some statistical observations, how the load pattern changes, etc. But we will not go to that level of statistical distribution, but I will say this much. Suppose for this distribution transformer, this information is known. What is that information? That is, for the first, I will make a column, time intervals. Very simple calculation, mind you. See, that is first T1 hours, T1 hours. Suppose day starts after midnight or say 6 a.m. say. From 6 a.m. we start counting. See, first T1 hours, I find that degree of loading, next column, degree of loading, I say it is x1, because it is not full load always. So, first T1 hours intervals, T1 in hours, hours, T1 hours, x1 is the degree of loading, and S is the kVA rating, S kVA is the rated kVA, rated kVA. Similarly, I will write another column I make, power factor of load. Suppose it is given as cosine theta 1. In the same way, I will do for the next T2 hours, let the degree of loading is x2 and power factor is cosine theta 2. T3, x3 is the degree of loading and cosine theta 3 is the power factor. In this way, I will say that the last Tn hours, xn is the degree of loading and cosine theta n is the power factor angle. This T1, T2, T3, this sigma T1 plus T2 plus dot dot Tn is 24 hours over a complete day, that I must see first 6 hours, next 12 hours, next 6 hours, such that it is like this. This will be the thing. So, what I have to calculate, and S is the rated kVA. So, energy output over 24 hours I have to calculate. Acha, next what I do is the copper loss. In the next column. In the first T1 hours, degree of loading is x1. So, what is the copper loss? It is x1 square into P copper full load. What is the copper loss here? x2 square P copper full load. This is x3 square P copper full load. In this way, this is xn square P copper full load. P copper full load is constant. At full load condition, what is the copper loss, which I get from short circuit test data. So, this is the copper loss at various time intervals taking place. What is core loss? Core loss, as you know, is independent on the degree of loading. So, it will remain P core all the time, no matter whether x is 0 or x is 1, x is 0.8, no. So, it is always P core fixed. got the point. These informations you need. Then you can straight away write down, I will write it here, all day efficiency as equal to what I told. I must write energy output over 24 hours. What is the output energy in the first T1 hours? What is the kilowatt output? It will be x 1 S cosine theta 1, this is the kilowatt, into T 1. Are you getting? Into T 1. In the first T 1 hours, so much kilowatt hour plus x 2 next T 2 hours. What is the energy output? X 2 is cosine theta 2 into T 2. This is not x multiplication, multiplication into T 2, x is here curly. In this way, you go on adding, x 3 you add, and finally, you add to this plus x n s T n, no, x n s cosine theta n into T n. So, over 24 hours, this is the energy output. Energy output. What is the unit? Kilowatt hour. Then below what should I write? This is the output energy. So, this bracketed term I am not rewriting, this numerator, this thing, this is the energy output, that is this thing here, plus the losses, energy losses. Now, the question is what will be the energy losses? See, of which you see the core loss remains constant all the time, it does not depend on degree of loading. So, it will be 24 into P core. How this 24 comes? It is in fact T 1 plus T 2 plus T 3 plus T n into P core, but that thing is 24. So, 24 into P core kilowatt hour plus. So, core loss will always take place in the distribution transformer plus the copper losses. Copper losses energy dissipated will be how much? I will write it in different color. It will be first T 1 hours, it will be x 1 square P C U full load into T 1 plus next T 2 hours x 2 square, because degree of loading changes full load into T 2 plus x 3 square P C U full load into T 3 plus last term x n square P C U full load into T n. This will be also in kilowatt hours. So, this whole thing is in the denominator. So, this divided by this will give you the energy efficiency or all day efficiency of a transformer. And it is based on this number, that is while purchasing a distribution transformer, you should rather tell the manufacturer, okay, this is my degree of loading pattern on the secondary of the transformer will be, and I would like to have energy efficiency of this much, rather than so your transformer has a specific rating, SKVA is the rated KVA, fixed voltage ratings are there, But you will say I do not like to have the maximum efficiency to occur at rated condition, knowing fully well that the load on the secondary of the transformer is not in my hand, it is going to change over time. And after doing some statistical observations, I have seen okay, on an average first T1 hours, so much demand of power, degree of loading is x 1, then degree of loading x 2, then, and power factors of the expected load on the secondary of the transformer at that time will be cos theta 1 for the first T1 hours and so on. And as degree of loading changes, copper loss in terms of rated PCU full load will go on changing, and I know how to calculate that, I will calculate. Core loss remains same. Only thing, instead of output kilowatt by input kilowatt, it is output kilowatt hour divided by this whole thing is the input kilowatt hour. What is the input kilowatt hour? This bracketed term, once again I have not repeated, it is this one numerator plus core loss remains same. So, what into hour? 24 hour plus this. Mind you, T 1, although it is written T 2 plus T 3 plus plus T n is equal to 24 hours. Okay, thank you. We will continue with this next time.